In this lecture, I will talk about Tip plasticity and small-scale yielding in fracture mechanics. Up until this point, we have developed certain relations regarding distributions of stresses at the tip of a crack. As a general case, we can consider a crack tip as shown here. Suppose that it's a crack tip, and we define a coordinate system, a polar coordinate system at the crack tip. However, asymptotic relations can be derived. For example, asymptotic stresses and displacements can be derived in terms of stress intensity factors, but they are valid in a small zone around the crack tip. I can show these as a zone around the crack tip, and suppose that this is the singularity dominated zone. Singularity dominated zone, which means that asymptotic representations of stresses are applicable here. They are a reasonable approximation to the actual sphere in the singularity dominated zone. That's shown as D, or domain D. However, linear elasticity analysis shows that stresses become singular near the crack tip. Therefore, around or in an even smaller region near the crack tip, we expect a certain amount of inelasticity, large strains, and other phenomena associated with non-elastic behavior. And in general, this is referred to as inelastic region. And in this zone, because of larger stresses, the material undergo yielding plasticity, because normally the stresses approach infinity near the crack tip, but we know that it's not possible. You cannot have infinite stress in a material. Therefore, there's a high probability of yielding in the small zone near the crack tip. And this zone or region is going to be denoted by R. However, in small-scale yielding assumption, asymptotic representations and linear elastic fracture mechanics, which is LEFM, is applicable if size of the inelastic region, size of the inelastic region is sufficiently smaller or much smaller than the size of the singularity dominated zone, the size of the singularity dominated zone, it's STZ. Under these conditions, the problem is generally referred to as a small scale yielding problem. And how can we find the size of the plastic zone? That's one of the questions we can consider. And we will look into this. We'll try to estimate the crack tip plastic zone. If this is the inelastic region, or the region in which plasticity occurs, how can I approximate the size of that zone? That's called crack tip plastic zone. And there are approximate methods to determine the size of the plastic zone. Again, we will consider a general case. That's going to be mode 1, a mode 1 crack. With length 2a, these are y and x-axis. Crack tip coordinate system is placed. And we know the asymptotic results, asymptotic representations. I think we can write them, for example, sigma y as a function of r and theta. It's k1 over square root of 2 pi r cosine theta over 2 times 1 plus sine theta over 2 times sine 3 theta over 2. It's an approximate representation or asymptotic representation for sigma y. It's written in terms of K1, mode 1 stress intensity factor. And let me write out of stresses as well. Sigma x near the crack tip. It's K1 over square root of 2 pi r. Again, cosine theta over 2. 1 minus sine theta over 2. Sine 3 theta over 2. Sigma xy K1 over square root of 2 pi r cosine theta over 2 sine theta over 2 cosine 3 theta over 2. These are known. Now, in addition to this, these results, you can write sigma z as well. What is sigma z equal to? What is sigma z? What is sigma z for plane stress? 0 for plane stress. And what is it for plane strain? Sigma z. You know how to evaluate it, right? Nu times is sigma x plus sigma y for plane strain. And I've said that you try to find the size of, or estimate the size of the plastic zone near the crack tip, which in general is shown as an inelastic region. Or that could be large deformations or strains as well. And as a first approximation, we can use the yielding criterion to find the size of the plastic zone. So what are the yielding criteria we can make use of here? Or which yielding criteria can you suggest? Yes, for Mrs. We will use for Mrs. yield criterion. Now for a first estimate, of the plastic zone size of the plastic zone size can be obtained by determining the locus of points where the asymptotic field satisfies the yield criteria yield criteria, for example, applicable for metallic materials. And for this purpose, consider von Mises yield criteria. And how do we write von Mises yield criteria? There are different ways of writing it, and we can write it in terms of principal stresses. For example, it's sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared equals 2 times sy squared. And you know what sy is? What is sy? Yield strength of the material And we have to determine principal stresses in terms of the asymptotic stresses. Principal stresses have to be found. First of all, I can find principal stress in the z direction or the turn direction, because if you think about stress distribution, let's say that is the crack tip again, and consider a stress element close to the crack tip, so and theta, and on an enlarged diagram show stresses acting here on this element. And we know what the stresses are. I mean, at least qualitatively, x, y and x, and xy, these are known. In z direction, what is the stress in z direction? Out of plane direction. It's either 0 or mu times sigma x plus sigma y, z. Now, this is sigma z. Sigma y, sigma xy, and sigma x, and sigma z. And because of planar elasticity, sigma yz and sigma xz are 0. Therefore, z direction, what can I say about the z direction? Sigma yz and sigma xz are 0. Therefore, the z direction is, what can we say here? One of the principal directions. That's right. Principal directions. And sigma zz is a principal stress. One of the principal stresses is found. It's either 0 or given by the plane strain result. And let's say that is the third principal stress. Let the third principal stress be equal to sigma zz. And how can I find the remaining two principal stresses if for any stress element like this, in plane stress elements? Yes, it could be possible. I can also use the available formula. If this is our element, I can find the directions, principal directions corresponding to this element. And the formula are already available for principal stresses as planar rotation. The element rotates in this plane. And from strength of materials, we know how to write principal stresses. And these are sigma 1, 2. Principal stresses for this case. Let me write it here. Sigma 1, 2 in this plane is equal to sigma x plus sigma y over 2 plus minus square root of sigma x minus sigma y over 2 squared plus sigma xy squared. Now, this is for rotation in xy plane. We know that these stresses are sigma x, sigma y, sigma xy. I can apply this formula. Apply. So these results say that 1, 2, and 3 substitute at 4.